Okay, let's go through that problem from our homework again. It was a little tricky, involves some calculus. We have a semicircular line of charge, it's positive charge. The circle makes the arc has a radius of curvature r, which means it's half a circle of radius r. The charge at the center is 1 electron, so the charge, I'll call it Q1, is negative E, the elemental charge. The radius is some number, I don't remember what it was, but it's given to you. And the linear charge density, again, it's some number, and that's in units of coulombs per meter. That means every meter has so many coulombs of charge. You find the length, you multiply it by this, you get the total charge. And the question is, find the net force on the electron at the center right here. Well, it's not as simple as dealing with point charges. We have a distribution, so we're going to have to integrate over that distribution. So you draw the situation again, and you note that some little piece of the charge line here, dq, it's a dq meaning an infinitesimally small piece of the charge q. Actually, if you want, I'll call it dq2, because it's an infinitesimally small piece of q2 being the total charge on that whole line. Well, since we're talking about an infinitesimally small piece of the charge, that's going to create an infinitesimally small piece of force. That's what the little d means. So dq2 interacting with q1 yields a differential force dF. So how do we treat that? Well, it seems a little bit more complicated, but really it's exactly the same way as if we had 2 point charges. Q1, if we had Q1 and Q2, then the force vector would just be the K Q1, oops, that's not a vector, sorry, K Q1 Q2 over R squared times the unit R vector. And of course, you know, if they're both positive, in this case one's negative, so that's going to be an attractive force. But we don't have point charges, we have the distribution, but we can take a little piece of the distribution and treat it like it were a point charge. So I'm going to come over here and I'm going to write the force vector is equal to K Q1 times, instead of Q2, it's going to be dQ2, because it's not a point charge, it's a piece of a distribution. And that means that this is going to be dF, not F, because it's only a piece of the force. It's only a portion of the force. And we're going to divide this by R squared. I'm using capital R to indicate I'm putting, you know, a known number in there. It's constant, no problem. The issue we have here is now we don't really know what dQ is, because we have no sense of what that charge will be. And that charge will vary depending on how big of a portion of this line we factor in. So I'm going to have to find another expression to put in there. dQ2, well, what's it going to be? Well, we do have the linear charge density, so if I just multiply that times the arc length S, where S is this arc length, then I've got the total charge, but it's not the whole arc length. It's a small piece of the arc length. So remember, we have to keep putting these D's in to indicate that it's only a piece of something, an infinitesimally small piece of something. Well, we need an expression for S, and if you may remember from rotational kinematics, anytime you have some angle theta, the arc length S subtended by that angle is equal to the radius times the angle subtended theta. So what I can do here is I can put in dQ2 equals lambda d, again a small portion, differential element of r theta. I just put this in here. But we know r is constant. R is not a piece of anything. It's constant, it's whole, it remains the same the whole time. So I'm going to pull that out of this differential element, and I'm going to make it a capital R to indicate I'm putting this fixed value of r in. And then that leaves d theta. Theta is the only thing that changes. Theta is what determines how much charge we have, because you know, if we make a big span, we have more charge. A small span, we have smaller charge. So I'm going to take this and insert that into our equation. Okay, all over r squared. So I'm going to make a few modifications. I'm going to plug in, we know Q1 is equal to E, so I'm just going to kind of get rid of some Q's to simplify some things. And we also know that we have r over r squared, that will simplify. So df equals k times E lambda d theta over r. Oh, I'm sorry, I forgot the unit vectors everywhere, because these are all vectors. Now here's the thing. This is in polar coordinates. This is determined by, this is in the direction of the r vector connecting one charge to the other. But it is not isotropic. So we are going to have to break this into df, and plus the question asks you to do this, so you know it leads you in that direction. df is equal to dfx, oops, that's not vector, I hat plus df y j hat. We're going to have to put it in that form. And one of the reasons we're going to have to put it into that form is, you know from trigonometry we're going to introduce more angles and everything else. And if we introduce more angles, that's going to have an effect on the charge and the force, because it's going to play into this d theta. Okay, so what am I trying to say there? If we have df is going to be a function of dfx, dfy, dfx equals, this is theta, df cosine theta, dfy equals df sine of theta. I'm going to bring this down here. I've got some more room. So that means the vector df is equal to df, which is k e lambda d theta over r times cosine of theta I hat. Oh, I'm sorry, that's actually going to be negative because it's in the negative x direction. So I've got to put that negative out there. Plus k e lambda d theta over r sine of theta j hat. Now here's the thing, in order to get, you may ask yourself, why is there not a negative here? Because when df comes down here, it's going to be negative as well. Well, you're going to see that's going to cancel out because of symmetry. Either you see that immediately and you put the y term equal to 0, or you'll see from the integration it's not going to matter. I'll show you here in a second. So in order to get the total force, you have to integrate all of this stuff. So you have to add all the little df's all around the electron, all the small portions of the force, add them all together, and of course every one of those df's corresponds to a dq, and a d theta. So we're adding up all of those things, and the way we add it is integration. So the force vector equals the integral of all the other force vectors and that is going to equal the integral of all this stuff. So I'll rewrite this. Negative k e lambda d theta over r cosine theta I hat plus the integral of k e lambda d theta over r sine of theta j hat. I'm going to write this differently. The only reason it doesn't change anything except I'm pulling all the constants out of the integral because they play no part of the integration. A constant does not affect the integral. So the force vector is negative k e lambda over r, and the integral of cosine of theta d theta, see how that moves in there, plus k e lambda over r, this integral, oh I forgot I hat, sine of theta j hat. Oops, I forgot d theta. Now these are definite integrals, so I should have put in here this is from theta 1 to theta 2. So the limits of the integration go all the way down from the theta 1 down here all the way up to theta 2. And remember, this is measured with respect to the x-axis. So this is theta. It goes all the way from theta 1, which is down here, to theta 2, which is on the top side. And I can write this out. Theta 1 is negative pi over 2. Or it's negative 90 degrees, whatever you I prefer working in radians. And theta 2 is positive pi over 2, which is positive 90 degrees. So we'll perform this integral. One thing that should be clear to you, though, is that we put in this cosine term, and this, even though it's not part of the dq sequence that we came up with up here, cosine of theta is definitely part of the force because this up a little bit. Every little piece of charge as you get closer to the x-axis has a greater effect on the force because, as we're about to see, the y segments cancel out. So this little small piece of charge here has no effect on the force whatsoever because it's canceled out by this over here. So the location of the piece of charge, not just the size of the span of the piece of charge, has an effect on the force. So anywhere you see theta, since you're going to have to integrate with respect to theta, anything involving theta plays a role in finding the force. So F equals negative k e lambda over r. The integral of cosine is sine. So I have to think about that backwards. The derivative of cosine is negative sine, so that means the integral of cosine must be positive sine. That's the way I remember it. And that is evaluated from theta 1 equals negative pi over 2 to theta 2 equals positive pi over 2 plus k e lambda over r. The integral of that is negative cosine of theta. Again, derivative of sine is cosine, so the integral of sine is negative cosine. Theta 1 equals negative pi over 2, theta 2 equals positive pi over 2. So I'll plug this stuff in. I can pull out these constants everywhere. Got my vector bar. Oh, I forgot my unit vectors too. Getting real sloppy. So this is negative, remember the negative sign right here, sine of pi over 2 minus a negative, which is going to become positive sine of pi over 2. And I'm just going to put the minus sign out here. That's going to follow everything. Minus, well, like that. Okay. Minus cosine of pi over 2 minus cosine of negative pi over 2. Well, now you see on the y side, cosine of pi over 2 is 0. So it didn't matter what sign we put in there. And we saw from symmetry that the y components are going to cancel each other out. And we see that that indeed happens. So negative sine of pi over 2, that's 1, so that's negative 1, plus sine of, that should have been negative pi over 2, which is sine of negative pi over 2 is negative 1, so it's negative 1 plus negative 1, so that's negative 2. Negative 2 k e lambda over r. That's our final answer. And you can put in the numbers from here.